today we will spend some time on reviewing what we have done so far and work out some problems in the area that we have discussed so far, so that you can understand the subject much more deeply, and also it will work as a test. So, what I do is I will work out some problems regarding transistor applications, and then I will also work out some problems using operation amplifiers, so that you can you will be able to appreciate the subject much more deeply. So, let us see the application of transistors first. So, for that let us take transistor as an amplifier. If we want to design a transistor amplifier, how will we go about doing that? Transistor as an amplifier. If we want to design a transistor amplifier, then I fix the spec. So, let me have the spec for the design. So, I want transistor amplifier, input signal is 0.1 volt, 0.1 volt, then I want amplification by a factor of 10. Amplification required is 10. Assume signal frequency is 1 kilohertz, then supply voltage, say we have say 10 volt is the supply voltage that we have, and then I have to have a load. For example, what is the load that it is supposed to deliver this amplified voltage. So, load load resistance is take it as 10K. So, what we want is we have to design an amplifier using a transistor. So, I have this amplifier stage here, and this input signal is given here, that is the input signal, that is in 0.1 volt and then 1 kilohertz. The output is here, the output supposed to be loaded to 10K. So, at 10K I should get 1 volt AC supposed to come out. So, how we go about designing this? So, if you look at the general transistor amplifier configuration, that looks like this. You have the transistor, then you have this resistance, and then the load collector load resistance, and then this is supply voltage plus 10 volt, and that is grounded here. Then we have the two biasing resistances. This is load supposed to be 10K, and this is the output voltage, and our input signal is supplied here. This is 0.1 volt, 1 kilohertz. So, this is our next that is the this is the actual circuit that we will be using here. And only thing is we have to decide on these resistances. Resistance value, say I will take it as R1, R2, or I will call RE. Then this is I will put it as R2, then R3, and then we have C input capacitor, C output capacitor we have. This one. So, we are now in all these designs, it is better to keep the operating point, that is this point, at mid value of the power supply. Power supply voltage is 10 volt. So, select this, I call this point A. So, without any signal, without any input signal, keep this point A at of the supply voltage. So, our policy would be that maintain A at V supply by 2, that is equal to 5 volt when V input is equal to 0. When there is no input voltage, then make sure that the point A is at 5 volt. That is the first step that we have to keep it. Now, to get that one, we have to select this R1 and RE, R2, R3 values. Now, first what we have to do is this 10K acting as a load when there is when we are applying a AC voltage here, when we are applying a AC voltage here, then we are getting amplified AC voltage here, and that AC voltage actually flows through this. So, this is acting as a load. So, when current is flowing through that, that current actually comes through that. So, effectively this R1 is getting loaded by this load, that is this 10K. So, we have to make sure that R1 is much smaller than this 10K, then only the loading effect can be minimized. So, normally factor of 10 is taken into consideration. So, to neglect the loading effect, that means if this is 10K, then obviously if this loading effect not to be seen means R1 should be 1K. So, our first step would be consider the load and then fix R1 10 times lower than that. So, fix R1 10 times lower than load which is 10K. That is in this case R1 is supposed to be 1K. So, I will fix R1 as 1K. Once R1 is fixed, then it is easy to fix RE, because the gain is actually given by the ratio between these two. Gain is ratio between R1 and RE. So, the R1 and RE ratio is the gain. So, since R1 is fixed, R key can be fixed. So, gain is R1 by RE. So, R1 is 10K. So, RE automatically comes to be 100 ohms. So, RE is fixed, R1 is fixed. Now, if it is if this is the case, then now we have to fix the other two resistors, that is R2 and R3. That is R2, R3, these two bias resistors, that is these two bias resistors to be fixed. Now, we know this is 100 ohms. That means, we have to find out what will be the voltage at the emitter. Now, midpoint, we have taken that this is at 5 volt, because A is taken as 5 volt. That is what our starting point. So, if this is 5 volt, when there is no AC here, then 5 volt, that means voltage across R1 is 5 volt. This is 10 and this is 5. So, if I look at this, so this point is at 5 volt, this is at 10 volt. So, voltage across R1 is 5 volt. So, current through this is resistance is 1K. So, current through this is 5 milliampere. So, current through this RE also almost 5 milliampere, because the neglecting the base current effect, then if this 5 milliampere current is going, 5 milliampere current is going through this. So, the next step is finding the current through RE. So, what is the current through RE? What is the current in RE? That is the question. So, the current in R1 is equal to current in RE. So, current in R1 is equal to R1 is actually 10 minus 5 divided by 1K, that is 5 milliamps. So, current through R1 is 5 milliampere. So, current through RE also 5 milliampere. So, current through RE is equal to 5 milliamps. So, current in RE is known. So, we can always find voltage across RE. So, voltage across RE comes, 100 ohms into 5 milliamps that is 0.5 volt. So, the voltage at Re is 5 milliampere. So, if I go back the circuit and see, now what we have got is that voltage at this point is becoming 0.5 volt. That is when there is no AC signal, voltage at this point is 0.5 volt is coming. Then we know that if this is 0.5 and this is supposed to be sitting at 1.1 volt. So, we call this VB, voltage at the base is 1.1 volt. So, we can write that, that is that actually brings that voltage at the base to 1.1 volt. So, voltage at the base of the transistor base is equal to 0.5 plus 0.6 volt, that is equal to 1.1 volt. So, we arrived at the base voltage. Then we had also find out what will be the base current, because we had now fixed the other R1 and R2. So, we know the now voltage at base. Now, I should know what is the base current, because our idea is if this current whatever is flowing through this, the current that is flowing through this must be much more than the base current to neglect the effect of the base current. Otherwise, we had to iteratively calculate, that is not required. So, we can find what is the base current. So, we know the current through this is 5 milliampere, because we had taken this voltage at this 0.5 volt, that means 5 milliampere current was flowing through this, 5 milliampere current is flowing through this. If 5 milliampere is the emitter current, then base current will be 5 milliampere divided by HFE. Say that is taken as I take 100 as HFE for the transistor, then we can calculate the base current. So, next we calculate the base current. So, base current calculation we have to do, that can be done like this. So, to find the base current. So, emitter current is known, emitter current divided by beta of the transistor is the base current. Base current. So, that means the base current comes out to be, the base current would be 5 milliampere divided by HFE. So, that is beta. So, that actually equal to 5 milliampere divided by 100. That comes out to be 50 microampere. So, we got the base current. So, once base current is known, I can decide on the the current through R1 and R2, because this R2 and R3 sorry. So, the base current is now taken as 50 microamps, that is the current that is flowing here. So, if this current should be smaller compared to this, means I keep this current as 500 microampere. So, current through R2 R3 need to be 500 microampere. So, I make current through now I find out current through the R2 and R3. So, current through R2 and R3. This is only decided, this is to be kept 10 times more than the base current. This can be kept 10 times more than the base current, that actually can be kept as 500 microamps are equal to 0.5 milliamps. So, now we are very close to our design, because now we got the R2 R3 current and then voltage across R3, that is if you see the circuit, the voltage across R3 is 1.1 volt. See the voltage across R3 is 1.1 volt, and we know the current through this. The current through this is 500 microamps. So, then we can find out the value of R3. Once value of R3 is known, R2 can be computed, because we know the voltage across R2, because this 1.1, if this is 10, then we know roughly 8.9 volt is what is there, and current through this is 0.5 milliampere. So, we can decide on R2. For example, if we take this 1.1 divided by 0.5 milliampere, roughly 2.2 k is coming here, and then this is actually roughly 9 volt, and then 9 volt divided by 0.5 milliampere gives us 18 k for R2. So, 18 k and 2.2 k will give me 1.1 volt here, and this amplifier will nicely amplify this voltage, that is the input voltage by a factor of 10, and the amplified voltage will, that is 0.5 volt, will be appearing across V0 with 180 degree phase reversal. So, voltage now we can complete the design. So, voltage across R3 is 1.1 volt, and the current through R3 is 0.5 milliamps. So, R3 actually comes 1.1 divided by 0.5, that is 2 milliamps, that equal to 2.2 k. Similarly, voltage across R2, that is actually 10 minus 1.1, that is 8.9 volt, and the current through R2 is again 0.5 milliampere. So, R2 comes 8.9 divided by 0.5 milliamps, that comes 17.8 k. So, 18 k would be fine. So, that is how the design goes. So, if we look at the values, so we will get R1 as actually 1 k, then Re comes as 100 ohms, then R2 coming as 18 k, and then R3 is coming as 2.2 k. That is how this amplifier is designed. So, one can work out in the same line depending upon the supply voltage and the signal level and so on. One can always find do the same design, but one should be careful that when the voltage at the collector, if you, for example, in this case this amplifier works all right up to some point, beyond which that it does not work. The limitation is that if I increase this by say increase this voltage to say 1 volt, then I expect to get here 5 volt 10 times amplified, that will be 10 volt amplified voltage supposed to come, and that cannot happen because the supply itself 10 and what we are kept is only 5 volt as a operating point here. So, this works at 0.1 volt and it gives you here 0.5. If I give here 0.2, then I will get 1 volt. Then when I try to go beyond that, then you will have problem, because maybe I will get up at the point here 2 volt swing or 3 volt swing maximum I can expect, not beyond that. So, you can go at the maximum 0.3 volt here at the maximum in this design. So, one can get different values of R1, Re, R2, R3 depending upon this supply voltage and the input voltage level that is expected, and of course, the load also plays a dominant role. Then only thing is that capacitors to be selected for C in and C out. The impedance of C1 and C2 must be small compared to the loads that they are seeing. This capacitor is seeing seeing this R2, R3 a parallel connector R2, R3 as a load resistance. So, the impedance of this C in should be much smaller at 1 kilohertz frequency compared to R2, R3. Similarly, the impedance given by this must be much smaller compared to the load resistance, so that not much voltage is lost. So, we have decided on C in and C out. So, how to decide on C1 and C in and C out. So, we had find C in what is the value and C out what is the value. So, for this to find what is the input impedance. So, the input impedance is impedance of the amplifier, impedance of the amplifier actually is going to R2 parallel R3, then actually you have a parallel 100 ohm into parallel 100 ohm multiplied by beta, that is also coming in, because when the if you look at the amplifier, I will redraw the amplifier here, So, if you look at the amplifier again, we have here 1 K and then this is taken as 18 K and this is taken as 2.2 K, this 100 ohms, and then we have to find this C out and this is 10 K, this is C in, this is 1 kilohertz 0.1, that is impedance, that is 1 by C omega should be much smaller compared to parallel combination of these two, and the reflected resistance of this emitter appears here, because if I draw the input impedance, there is nothing but parallel combination of this and then reflected resistance of this 100 ohm. The reflected resistance of the 100 ohm is 100 into HFE. So, the input looks like this, the input circuit looks like this. So, you have this source with this impedance, then you have the 2.2 K parallel 18 K and then parallel this 100 into beta, that is actually 10 K. So, in this case if you see this 2.2 K is a dominant, because if we take the 10 K and 18 K, that is much higher than this 2.2 K. So, one can take roughly 2 K as the impedance of the input impedance of the source. So, we take this is equivalent to 2 K. So, input impedance is is 2 K. So, the capacitors should have much lower impedance than 2 K. So, 10 times lower. So, I can take 1 by C omega. So, 1 by C omega should be 200 ohms, 10 times lower I had taken, and the omega is actually 2 pi into 10 power 3, 2 pi f at 1 kilohertz. So, one can find C. So, you will get 1 by 200 into omega, that comes as C. So, you will get 1 by 200 into 2 pi into 10 power 3 comes as C input rather, C input. So, if I take this one, that actually comes 1 by 10 power minus 5, this 3 plus 2 5 gone. So, you have 2 into 2 pi will be here. So, that will be 10 power minus 5 divided by 4 pi, roughly 12 it comes. So, you need this 10 power minus 5, sorry, 10 power minus 5 by 4 pi. So, that will be 10 power minus 6 roughly farad, that is 1 microfarad is required for C in. So, we can decide C in as nearly 1 microfarad is what is required. Similarly, we have to calculate for C out. So, calculation for C out. So, the equivalent circuit is that you have a output voltage passing through this resistance C out and going to 10 K, that is a C out. So, C out should be much smaller than 10K. So, roughly C out supposed to come 10 times lower. So, I will put it as 1K. So, the impedance of the C out would be 1K. Supposed to be 1K. So, that 1 by C omega comes to be roughly 10 power 3. So, we will get, and omega is as usual that 2 pi in 10 power 3. So, you will end up 1 by C into 2 pi into 10 power 3 is equal to 10 power 3. So, you will have 1 by 2 pi into 10 power 6 as C coming in. So, that actually comes out to be 10 power minus 6 divided by 2 into roughly 3. So, 10 power minus 7 into 10 by 6, that is 1.4 into 10 power minus 7, which actually turns out to be so the C value comes out to be C out, rather C out comes to be 0.14 microfarad. So, we have now arrived at all the values for the circuit. So, if you look at the amplifier design now, it looks like this. You have this, you are connected here 100 ohms, then here we have to put 1K, then here you have put 0.14 microfarad, then we have the load resistance of 10K. This is given plus 10 volt, that is ground, and we had these two resistances. This is 18K and this is 2.2K, and then have this and apply the voltage here, and this is put as 1 microfarad. That is how the circuit design is completed. So, the amplifier can be designed step by step using this procedure, so that the required performance is obtained. Of course, we have not drawn the equivalent circuit of this transistor by taking care of Miller effect capacitor and so on. That is not required right now at this point, because nowadays we do not design this kind of amplifiers, which because we normally use operation amplifiers. This is only to illustrate how the amplifier is working. We have done this exercise. In actual case, actually we have to consider there is a capacitance across this, and because of this capacitor, the output voltage partially fed back to this, and then that applies the voltage here, reduces the voltage at this point, that also reduces the voltage at this point. But this capacitor effect is not significant at 1 kilohertz. So, one need not worry about that. In high frequency amplifiers, they do not have to worry about the effect of this as well. So, at this point we are not looking at the design of high frequency amplifier. So, we are not bothered about this capacitor effect. Now, let us see another design example, namely how to use the transistor as a switch and for switching applications, so that we can use the transistor along with probably the MOSFET at very many different places in analog circuit as a switch. So, for example, I want to drive a relay. For example, driving a relay using a transistor, we look into this design at this point of time. So, how to design a relay driver using transistor. So, the circuit that we are thinking is like this. We have a relay, assume this is a 12 volt relay and I have a supply of say plus 12 volt, and then this relay is actually nothing but you have a coil and then it has a contact. So, when coil is energized, the contact is pulled closed, when the coil is switched off, the contact is open, so that this contact can be used to carry some load current. So, for example, I can put a load like this. So, whenever the current flows through this coil, this contact will be energized and the current will be flowing through this. When you stop the current flowing through this, the contact will be open and the relay will be off. So, this is the relay part actually. So, this is to be switched on and off using a transistor. So, I can use this, I can put this, then now we also have to have this. I will explain about this use of this diode. Without this diode, the transistor invariably goes bad. We put this, then we have a signal coming in, if the, for example, another operation amplifier assume is there, and that gives you the signal to switch on this. So, when this is high, it will be plus 15, when this is low, it will be minus 15. So, we want when the output is plus 15, the relay should be on, when the output is minus 15, relay should be off. That is what we are planning to do. So, writing the problem statement, actually what we want is, I will put a point here, okay, I write here, that is when V output of op amp is plus 15, relay should be on. V output op amp is minus 15, relay should be off. Relay should be off. So, assume the we had given out the that means how will you complete the circuit. So, I had to complete the circuit by linking the base to the link this one to the base. So, I will put one diode, then plus I put one resistance here. So, I call this is R1, this is R2. So, the diode you have two diodes, D1 and D2. So, D1 actually when the minus comes, it does not allow the voltage to go in, go to the base. When it plus 15 comes, it allows the voltage to go on, then that will switch on this. Now, only thing is we have to select what is the value for R1 and R2, then we also should explore why you need D2. So, of course, without D1 also it can work, but it is not a good design, banging a minus on the transistor, and if the transistor base center voltage exceeds 7 volt, most of the transistor actually goes bad if the current is not limited. Of course, you have a current limiting resistance here, of course, so it may not go bad, but nevertheless it is not necessary to design like that. It is considered as a bad design, banking minus on the transistor which is not required. So, we had decided basically R1 and R2. Now, for this to decide, we should know what is the current that base is taking. So, we should decide on the base current. Now, base current we have to decide, then I should know the collector current. So, without worrying about temperature, I will first fix what is the collector current required. So, we have to find the collector current of the transistor. Collector current of the transistor. So, that is actually collector current is nothing but the load current, relay current. So, collector current is nothing but a relay current. Now, the relay current is given by the relay manufacturer, because only if that much current flows, the relay will be activated. So, assume the relay current is in this case, let the relay current be current be 100 milliamps. So, we need 100 milliampere current that to flow through the relay, then only the relay will activate the contacts. So, taken the relay current. So, now once relay current is known, the collector current of the transistor is known, that is 100 milliampere. So, IC collector current is actually 100 milliampere. Then transistor base current, that will be IC by beta, that will be 100 milliampere divided by, assume beta is 100, then it will be 1 milliampere. So, you end up in having a base current of 1 milliampere in this design. So, once base current is known, then it would be easier to decide on the two resistors, that is R1 and R2, because now this current is known. So, this current is 1 milliampere. That means if it is 1 milliampere, and then we know when the transistor is on, this voltage is 0 volt, we grounded, and this will go to 0.6 volt. So, if this is 0.6 volt and we know the current is 1 milliampere, the same 1 milliampere current is flowing through that, and then we know the this resistance R2 is used only to discharge the when the voltage goes minus, this becomes 0, but then storage charge in the transistor, that is the base emitter, you have a capacitance that to be discharged, for that only we are using R2. So, the R2 is actually can be large, there is no problem, because for example, if this is a few PF capacitor, taking R2 say for example 10K makes the discharge time is of a few millisecond or even less than that, it will be only few nanosecond. That kind of off time is fine, because the capacitor of 100 PF and then 10K, 100 PF is 10 power minus 10, 10K is 10 power 4. So, you will have a switching time of 0.1 millisecond. So, if the capacitance base emitter capacitor is 100 PF. So, for base emitter capacitor, cap of 100 PF for R2 is equal to 10K, then switching, then off time comes to be 10 power minus 10 in 10 power 4, that comes 10 power minus 6 seconds, which is quite fast. So, need not go much larger than 10K. So, if it is not enough, we can readjust, because this R2 is in our control, this is our selection. So, we can select even larger value if the time is very short. So, this is fine. So, R2 is fixed. So, we got R2 as 10K. So, which leaves us only to decide the other resistance, that is R1. So, because this resistance is 10K now, and we have decided on this value now. Now, this is a 10K, that means this voltage across at this point is 0.6 volt. So, current through this is 0.6 by 10K. So, current, this is 1 milliampere current is going, and here 0.6 by 10K. So, the current here, the current I here would be 0.6 divided by 10 power 4, that will be 0.6 into 10 power minus 4, that will be equal to 6 into 10 power minus 5 amps, that will be equal to 60 microamps, or in milliampere wise that comes 0.06 milliamps. That is the current that is flowing when it is on. So, if this is at if this current is 1 milliampere, this current is 0.06 milliampere, then total current R1 will be addition of these two. So, the total current R1, so total current R1 through R1 so the base current is 1 milliampere, current is 1 milliampere, then the resistance R2, R2 is 10 K. So, current through R2 is current through R2 is actually 0.6 by 10 K, that was worked out to be 0.06 milliamps. So, total current through R2, total current through R1, through R1, that is equal to 1 milliampere plus 0.06 milliamps, that is equal to 1.06 milliamps. Now, we have to select the value of R1. So, for that to know, we should know what is the voltage across R1. So, if you look at the circuit, the voltage across R1 is voltage across R1 we have to decide. So, that means we have to find the voltage across R1. So, if you look at the voltage across this R1 we have to find out. So, if this operation amplifier is operated with plus 15 minus 15, normally we will get up to 14 volt here. When it is fully on, you will not get 15, normally 2 diode drops less. So, you will have around 14 volt here and 1 diode drop is lost here. So, you will have here at this point roughly around 13.4 volt, and this point is sitting at 0.6. That means the across the R1 resistance, at this end we have 13.4 volt, at this end we have 0.6 volt, that is at this point we have 13.4 and at this end we have 0.6. So, voltage across R1 turns out to be 13.4 minus 0.6, that is 12.8 volt. So, we will then once you know the voltage across this is 12.8 and I know the current flowing through this, which is 1.06 milliampere. So, I can write 12.8 divided by 1.06, that roughly around you get around 12 K resistance. The 10 K standard resistance available, that can be used here. So, if that means R1 needs to be around 10 K. So, that we can do it like this. So, if you show the calculations, it works out to be like this. So, voltage across R1 is actually 15 minus 1.2 volt, that is across the voltage across the, that is lost on the op amp, minus 0.6, that is on the diode D1, then minus 0.6, that is at the base voltage, that is the voltage across the R1, which works out to be 15 minus 2.4, that turns out to be 12.6 volt. So, current through R1, that comes out to be 12.4, that's 1.06 milliamps. So, we can write R1 is equal to 12.4 divided by 1.06, that I can roughly take it as 12 K, this is milliamps. So, I can take R1 as 10 K, the 10 K what you get a standard value, because it should be little lower than 12 K, then only even at high temperature you will able to supply the enough current. So, R1 to be decided like this. So, we had shown one example for switching, that how to design a transistor circuit for switching, because this kind of switches are very often used nowadays in analog circuit. So, to switch on off a relay or some other circuit. Now, we actually do one more design such that we will understand this circuit design much better. For example, we can do the same design using a MOSFET. For example, I want to drive a MOSFET I want to drive a relay using a MOSFET. So, how will we go about designing this? So, relay drive using a MOSFET. So, the general circuit looks like this. Then I can have this. So, I have this, then assume the same operation amplifier circuit there which gives me the voltage. So, I want to drive the MOSFET here. So, I connect minus I do not want to apply. So, I can do this, I can put connect this one directly, because it is not a current operated device, it is a voltage operated device, and this is supposed to be a relay. So, I remove this resistance, I connect the relay. One small this thing I did not explain what happened in the other case, what is the function of this diode. So, in this design I will explain the function of this diode in detail. So, we have this one. So, when it is plus 15 volt, when it goes high you will almost get around 14 volt. So, this is 14 volt you will be getting, and then after one diode drop you will get about 13.6 volt. So, the MOSFET will be on and we need not worry about the current. Then when this goes to minus when goes to minus say 14 volt, then this diode will be off and you will get no voltage here, but then the diode will not allow, but the MOSFET is having a capacitor and that capacitor can't be discharged. So, even when it goes minus 14, this capacitor will be holding the charge and MOSFET will be continuously on, it will not go back. So, we have to provide a path for the MOSFET to on go off. So, we have to give one resistance here, because here we are not bothered about the switching speed, because we are switching the relay once in a while, once in few seconds or once in a minute only we will be switching. So, the switching time can be few milliseconds, is not a problem. So, the switching off time would be this capacitor, for example, if it is 100 pf, and then if I, for example, if I have 10k resistance, then the time would be the RC time, that would be equal to 10 power 4 in 10 power minus 10, that will be 1 microsecond, 10 power minus 10. So, the time constant actually comes out 10 power minus 6. So, in few microsecond time, in a few time constant it will discharge. So, off time will be only few microsecond, that is good enough for this application. For example, we have a MOSFET BS170 is there, which switches on at 5 volt, 15 volt is not a problem, and then the going off is done by this. So, using a MOSFET, designing a switch function is easier, but one problem when using MOSFET is if the supply voltage is small. For example, if the supply voltage the circuit supposed to operate in only plus or minus 2 volt or 3 volt, low voltage applications, then the output voltage what you get will not be enough to drive the MOSFET, because if you get only 2 volt, with 2 volt the MOSFET will not be switched on, whereas transistor needs only 0.6 volt to make it on, the base end voltage needs only 0.6 volt. So, even low voltage applications you will not able to use MOSFET to switch on and off the relay. So, in high voltage applications it can be MOSFET can be used, because even BS170 needs minimum 5 volt to make the MOSFET on, and then with 15 volt it can take up to 15 volt. There is no problem actually applying more than 5 volt to this circuit, as long as we are not exceeding 15 volt, this is perfectly alright. Only thing is, now I have to explain what is the function of this diode, which we have not done it even in the other case. So, now we will explain what is the purpose of this diode. So, what you do is function of this diode, say D2. So, what is the function of diode D2? what is the use of D2? Actually, if you do not use D2, we already explained that this MOSFET or the transistor which is used in the previous example actually goes bad. So, what we do is that we explain the mechanism behind what is happening here. Suppose if I have a switch here, either MOSFET or transistor, and if I have the say for example supply is here plus 15 volt or plus 12 volt, then when the switch is on, then the current flows through this, and then this relay has a current capacity of 100 milliampere we set. This relay is having current capacity of 100 milliampere, and if this operating voltage is 12 volt, then in actual case the resistance of this coil, the relay has a coil actually, the resistance, the coil relay is a coil and the coil has a resistance, and at 100 milliampere actually if it is a relay specified 100 milliampere and 12 volt, then the resistance of the coil, the resistance of the coil would be resistance of the coil would be 12 divided by 100 milliamps, that will be 120 ohms. So, the resistance of the coil, so R the coil is 120 ohms. So, when you switch off, and then it also has an inductance. So, if you look at the circuit, then it looks like this. We have here 10 volt at this point, 10 volt 12 volt sorry, this relay is operated with 12 volt. So, this is 12 volt and this is 120 ohms, and this is at inductance, and when switch is on, the current flowing through that is 100 milliampere, because after a long time then current flowing through that will be 12 by 120, that is 100 milliampere, that is the current that is flowing through this. And then if you look at this, there is a current flowing through the coil, and then there is a it has a inductance. So, that energy stored in the inductance is half Li square. So, energy stored in the inductor is half Li square. So, when current is flowing through that, the energy stored, if we take the inductance, it will be about 40 to 50 millihenry inductance will be there, and I is 100 milliampere. So, certain amount of energy is stored in this, and then the current is flowing like this. When you switch off this, for example either MOSFET or transistor, if I remove the, for example if it is a transistor, I put the okay. So, if I redraw with the transistor, then you have the inductor and then you have the transistor here. It is shown this. So, when the current 100 milliampere is going, when I switch off, that is I remove this voltage to 0, take it to 0, then this transistor goes off. Then whatever current that is flowing here cannot go anymore in this. That means, when current was flowing, magnetic field was built up in the coil, and that energy is actually stored in the magnetic field. Now, I switch off this, then the whatever current that is flowing through this, I have to find cannot go through this, because the switch is not allowing that current to flow. So, you are trying to interrupt this flow of current, that means the current start decreasing, but then decreasing current will produce a decreasing magnetic field, because when current decreases, the magnetic field also will decrease. Then decreasing magnetic field will induce a voltage in the coil, that is a self induced voltage. So, as soon as I start switching off this, the magnetic field started collapsing, and collapsing magnetic field induce a voltage in this coil. That polarity will be actually aiding the input voltage, that if I draw that polarity will look like this. If I remove this and draw the decreasing magnetic field and then draw the voltage, that means I remove that, and the decreasing magnetic field will putting a voltage, this is the voltage that you applied, and then the decreasing magnetic field will apply a voltage like this. This is nothing but L into di by dt, that is the voltage induced in the coil because of the decreasing current, because current is decreasing, and then because of that it is inducing a voltage. So, now if I switch off this, the voltage at this point is sum of this voltage and this voltage. So, this is actually 12 volt, this is actually 12 volt. This actually depends on what rate that it is switching, what is LDA by dt. Assume the L is say 50 millihenry. So, L is if I take 50 millihenry, then into dI by dt is the induced voltage. So, if I take that, then dI by dt I can take, for example, this transistor switches off in 1 microsecond, that is how we decided earlier. So, if the switching off time, that is dt is actually 1 microsecond, then current actually the change is actually 10 power minus 1 amps, because that is equal to 100 milliamps, because the relay current is 100 milliampere. We are trying to switch off 100 milliampere current in 1 microsecond. So, that comes out LDI by dt if we calculate, so if we calculate LDI by dt, that comes out to be 50 millihenry if I had taken, then current of 100 milliamps, 10 power minus 1, and dt is 10 power minus 6, that works out to be 500 into 10 power 2, that you will get 5000 volt. That actually when you try to switch off the inductor abruptly, then you get this induced voltage going up to 5000 volt, and such high voltage this transistor can't withstand, because VCE breakdown voltage will be few hundred volt only we would have selected, and a 5000 volt destroys this transistor. That actually means that if I am switching the device like this with the transistor with the inductor with this switch, then you get a very huge voltage at this point, and that will make the device to go bad. So, if I want to protect, then I have to use a diode here to protect this. Once I put a diode, the problem will get solved, because now when I switch off the switch, whatever current that is going here trying to flow like this, because when the inductor, the current, when you are trying to break the current, then as I said, it induces a large voltage, and that voltage is positive here. So, once this voltage goes, if this is 12, if this goes more than 12, then this start conducting, this forward bias. If this is 12, and if the once I switch off, the voltage trying to go up, this once moment it goes more than 12, then this start conducting, it start conducting. So, that current will go like this and then go like this and continue to flow, and in this resistance, 120 ohm, the heat is the energy is dissipated out. It will take some time to circulate and dissipate all the energy, but nevertheless voltage at this point will not go more than 12.6, because this is 12 and this will be limited to 12.6. So, the device will not go bad. That is how that is the use of this diode. So, in this class we have discussed how to use the transistor to amplify the signal, and how to design various values to go with that, and also we had shown how to use the transistor as a switch and how to use the MOSFET as a switch, that also we had shown in this class, and I also explained you what is the use of the diode which is to be connected across the relay coil, also explained. So, with this I will stop. The next class we see other worked out examples. Thank you.